Hello everyone. In this video we're going to explore how to express an equation given to us in polar form in its rectangular form equivalent in terms of x and y. So the first polar equation we're going to look at is that of r equals 6. If you think about what that polar graph would look like, imagine a set of points where the r value is always 6. And in polar graph, remember that means we're going from the pole. We're going to go out 6 units from that pole. And imagine doing that all the way around, thus generating the graph of a circle. So we know that's what the graph's going to look like, but now let's take a look at the rectangular form equivalent. We're going to be using those equations we learned earlier in the lesson. And one of those states that x squared plus y squared equals r squared. So solve for r, we would have that the square root of x squared plus y squared is equal to r. That is what we're going to substitute in place of r. Squaring both sides of the equation then, we arrive at x squared plus y squared equals 36, which we know from algebra that that is the equation of a circle centered at the origin, 0, 0, with a radius of 6, thus confirming what we know the graph to look like also in polar form. Let's take a look at another one. In this one, we're given that theta is equal to pi over 4. Again, think of what that would look like on a polar graph. We want the set of points where the angle is always pi over 4. Well, we know pi over 4 is right there. So if we think of the set of points all along that angle and extending into the opposite side of the pole, we end up with the graph of a line that goes right through the pole. It makes sense that when we find the rectangular form of this, we probably should have a linear equation. So let's see how we get that. Once again, we're going to use one of the formulas we had earlier, that being the fact we know tangent of theta is equal to y over x. Well, we know theta is pi over 4. And hopefully you recall from your unit circle knowledge that tangent of pi over 4 is equal to 1. Solving this for y, we simply get that y equals 1x, and think of it as plus 0. There's your y equals mx plus b form. So it is indeed the graph of a linear equation, and we know from our algebra this would be a line going through the origin with a slope of 1. Let's take a look at another. Here we have r times sine of theta is equal to 2. This is an easy one because if you remember one of our earlier equations, we know that y is equivalent to r sine of theta, so we simply make that substitution and we have y equals 2. We know this to be the graph of a horizontal line. So why don't we try to graph this in polar form? We'll take a look at it on our graphing calculator, and you'll see that it does still, even in polar form, yield the graph of a horizontal line. If we solve for r, we would have 2 divided by sine of theta. Remember that in polar mode, when you hit your x button, you get a theta. And let's just do zoom trig to graph it, and there is the horizontal line we expected. The next one we're going to look at takes a little bit of work and creativity to get this one into rectangular form. Keeping in mind that we want to be able to utilize those equations that we had earlier. Remember, we've had x squared plus y squared equals r squared. Well, we only have a single r here. We know that y equals r sine of theta. Well, we have a sine of theta, but no r. And we know x equals r cosine theta. And again, here we have a cosine in the equation, but no r. So what we're going to do is multiply through by r throughout the equation. As we do that, we have r squared on the left, and we'd have on the right r cosine theta plus r sine theta, because we would be distributing that r across that sum on the right side of the equation. Once we have it in this format, now we are able to utilize those equations. In place of r squared, we would have x squared plus y squared. In place of r cosine theta, we know that's equivalent to x. And in place of r sine theta, we know that's equivalent to y. Bringing everything over to the left side of the equation, we end up with another form of what would be a circle. And we could easily graph this in polar mode. In rectangular mode, as we talked about in the earlier video, we would not really be able to solve this for y, thereby utilizing our calculator to graph it. But in polar mode, it's very easy. So let's go take a look at that. Returning to y equals, if you clear that out, and we'll simply type in cosine of theta plus sine of theta. And let's do zoom square, because we've seen earlier in problems we've looked at on our calculators, if you don't do zoom square, you don't necessarily get that nice circle. And there you go. It is indeed a circle. The next problem we're going to look at is another angle problem. In this problem, we have theta equals 2 pi over 3. So again, if we think about what this would look like, it's going to be very similar to the angle problem we looked at earlier. If we imagine the set of points all at the angle of 2 pi over 3, extending through the pole to the opposite side, we once again end up with a line. So when we're done, we expect we should have a linear equation. This one, though, looks like it has a negative slope. So we should somehow, once we have our linear equation, see that it does indeed have a negative slope. So we're going to use that equation that tangent of the angle would be equal to y over x. Recall that the tangent of 2 pi over 3 is negative square root of 3. Hopefully that's one you have memorized. Solving for y, we get that y is equal to negative square root of 3 times x. Think of that as plus 0 there. And there's your y equals mx plus b form, your slope-intercept form of a line. It has a slope of negative root 3 passing through the origin, confirming what we know the graph to look like in polar form. So moral of the story, anytime you have an angle that is given to you as a polar equation, the rectangular form is always going to be a linear equation. The last one we're going to look at is similar to another one as well. Here we have r equals 2 secant theta. This one you have to be a little creative again. Let's rewrite secant as the 2 over cosine theta. And if we multiply both sides by cosine, we have r cosine theta equals 2. Well, we know r cosine theta to be equivalent to x equals 2. We know that to be the graph of a vertical line. You might remember, though, on your graphing calculators in rectangular mode, regular function mode, you cannot graph, really, a vertical line, but you can in polar form. Returning to r equals, let's type in 2 divided by cosine of theta. We can do zoom trig. I don't think the window is going to matter, but there's the vertical line we expected, knowing that the rectangular form of the equation was x equals 2. So hopefully through all these problems, you've seen a nice breadth of the various kinds you might see. You've also seen the relationship between what the polar graph looks like and the rectangular graph and how connected they are. And hopefully this will allow you to move forward, do many on your own, and appreciate that connection we know to exist between the polar form of an equation and its rectangular form.